Yes, for giving me an opportunity to talk here. So title of my talk, as you see, that phase-shifted planar Hall magnetoresistitivities in oil semi-metals. So this is another kind of material where you have chiral symmetry broken, and this has a property that it gives planar Hall effect because of the chiral symmetry breaking. And that is actually the anisotropic that has been observed in experiment also. But what I will show that thing has some phase shifted form, which has not been looked seriously by both theorists and experimentalists, that I will trace upon. So the work has been, you can see here in this archive, and has been done by my former student who is in postdoc in University of Toronto, Sandeep. Okay, so bit of introduction to what the oil fermion is. So you start with spin half with non-zero mass. So that obeys the Dirac equation, as you know. So this is the Dirac equations, and this the solutions of that Dirac equation has 4 components: 2 spin components for particles and the other for 2 antiparticles. And that solutions will be the eigenstates of helicity, which is sigma dot p, but not of spin, and that will have left and right handed helicity. But when this becomes massless, so spin half particles with 0 mass, that obeys the oil equations. So this is now left-handed and right-handed chirality gives the 2 equations that it's satisfied by 2 equations by 2 types of fermions. These are called oil fermions. And these 2 component spinors, a definite chirality, they will have left and right chirals. And in this case, helicity and chirality coincide. Okay, so Dirac fermions you can think of as a combinations of 2 oil fermions of opposite chirality. And this oil fermions which is found by Adler, Bell, and Jackie, is called famous anomaly is called chiral anomaly. So if you do the classically treat the electromagnetic field, then you have for Dirac fermions couples to massless Dirac fermions. Then you have 2 types of conserved currents. One is the normal charge current, and there is the chiral current, which is mu5. But when you do quantum theory, they found that this chiral current no longer conserves, and then non-conservation is proportional to the E dot B, which is called famous chiral anomaly. So electromagnetic field drives because of that, so it drives changing populations of fermions of opposite chirality. So that never have been found in as a particles. So initially thought that neutrino might be the oil fermions, but later it was found that neutrinos have mass. So there is no fundamental particles like oil fermions. But fortunately, that have been observed in our solid state systems, where you can see some kind of physics of oil fermions in tablet of experiments. So oil semi-metals. So this is a cartoon of oil semi-metals. You can see that so they have Dirac line nodes. But so the chirality has been differentiated. So this is left-handed chiral, Dirac-like equations, Dirac-like dispersants, and this right-handed chirality of Dirac-like these things. And so if you just see it, what I have written here, so these exhibit linear dispersion near oil nodes, similar to massless Dirac fermions, that is oil fermions. And then there is a conduction and valence band intersect at oil nodes. These are oil nodes. So these appear as pairs with opposite chirality. So you always come with pairs. They may have many, but they will come as a pairs. So like here, left-handed, right-handed chiralities. And this act as a diverging and converging monopoles in Berry curvature. So Berry curvature is something like magnetic field in momentum space. And this leads to a topologically protected surface states, so known as the fermions. So there is a surface states also, it's called fermions. So this is a topological material. And these materials show some distinctive features as a chiral anomaly. So when magnetic field parallel to electric field, that induces pumping of electrons from one chiral node to the other chiral node. And so that gives some features in transport. So one of these things are resistivities are anisotropic. So anisotropic in the angle between the electric and magnetic field. And so this is one property. And the next is that one finds negative planar magnetoresistance, the second one, and third one is the planar Hall effect. So these are the three features that one has observed in transport in oil semimetals. So these are the papers where the planar Hall effect was predicted in oil semimetals. So this is the Hamiltonian for oil semimetals. So I have written here by purpose is a tau because I calculate conductivities, that is a sigma notations. So usually always its convention is k dot sigma. Instead of that I have written k dot tau. So the chi is the chirality, which is plus or minus 1 depending on left and right handed. So using this Hamiltonian, the calculated conductivity is sigma xx and sigma yx, which is the planar Hall. And it depends on, you can see that Berry curvature. And this has been done with Boltzmann transport theory. So there is, you can see that there is a tau there, relaxation time tau, not that same tau. This is space for the two-level system. So this is the tau here. And they found the conductivities. So it is sigma xx, which is a anisotropy, which is cos square theta. There is a sigma perpendicular, which is a Drude conductivity, sigma perpendicular. And then there is a something delta sigma in cos square theta. And in yx, the Hall, this is delta sigma sine theta cos theta. And then delta sigma, it has been predicted to be square of the magnetic field. And delta sigma is, so if you measure the diagonal transport when electric field and magnetic field is parallel, which is sigma parallel, and if they are perpendicular, so the difference between these two is the delta sigma. Okay, so as you see this, so this is kind of, there is a periodicity in theta that has been predicted. So if we see it, what about the resistivities? So the rho xx is one of our sigma xx, although this is the matrix, but since the Drude conductivity is larger than the other conductivities, so essentially the rho xx is 1 over sigma xx, which becomes rho 0 minus delta rho cos square theta. So rho 0 is the Drude resistivity, and delta rho is the delta sigma by sigma perpendicular square, and that is also proportional to b square. And sigma yx, which is sigma yx by sigma perpendicular square, which is delta rho sine theta cos theta. So conductivity and resistivity has similar form, only difference is that here it's negative. So it suggests that the magnetoresistivity is always a negative for the planar Hall, as far as the Boltzmann transport theory goes. So always negative, and these will be always proportional to tau. That is, I mean, the conductivities are proportional to tau. These are inverse. So the main features here, the magnetoresistivity is negative definite, as I said here. And then planar Hall resistivity, which is here, equals to sine theta cos theta. As you can see here, there will be the extremum at theta equals to pi by 4. So that's the prediction. And magnetoresistivity and Hall resistivity will be proportional to the square of magnetic field. That's it. So there are three predictions here from the Boltzmann transport theory. So if I see the experiment, so here you see that in this experiment, the magnetic field, there is an angle with the plane theta, and there is a perpendicular to the z. So when this theta is large, so it's closer to the perpendicular type thing, so you have the magnetoresistance resistance is positive, but it becomes negative when the theta is smaller and also at 0 angle. So you can see that magnetic resistance is negative here. So that's good. And then there is an oscillations also of Hall resistivity, rho xy. You can see here, Hall resistivity also there is periodic in theta. So the prediction was at the minimum on the extremum at 45 degree. Okay, so this material CD3AS2 is not the oil semi-metal, this is the Dirac semi-metal, but that can be converted into a weak oil semi-metal when you apply a perpendicular magnetic field. So if you have some small amount in this experiment, there will be some small amount of perpendicular magnetic field that makes the Dirac semi-metal into oil semi-metal. And if you notice here, the minimum here in the Hall resistivity is not exactly 45 degree, very close to that, but slightly away from it. Okay, so this is another set of another experiment. As you can see, the magnetoresistance is at 0 degree. So here the angle is only in the plane, not in the perpendicular. So only in the plane. So magnetoresistance, you can see that here it's negative and then becomes positive also. So it's not that it's always negative, it can become positive. So it looks like quadratic, that is fine. So there is a magnetoresistance changes sign, the planar magnetoresistance. And then this Hall resistance, you have a slightly shift from 45 degree also, but it's not much. Because this is the same system, CD3ASO2, which is very weak oil semi-metal. Okay, so unfortunately, the data that has been shown here where rho xx and rho xy both are present, that is only for CD3ASO2, not for other materials. So I could only show here CD3ASO2, but here there is another material TAS, where you can also see that magnetoresistance changing sign about 90 degree. You can, so it's from negative to becoming positive here. So from all those data, so what we can find, we can conclude that, or we can see that what are the features. The following features are not captured in semi-classical Boltzmann transport theory, as you can see from the experiment. So what is that? A change in sign of planar magnetoresistance. So that is one thing. Another thing, the extrema of planar Hall resistivity is away from expected 45 degree from theory. So these are the two features that are not explained through Boltzmann transport theory. So we took up this problem and we thought a different way. Okay, first of all, I can show the symmetry principle here. So this is a wild semi-metal Hamiltonian, and let's say wild semi-metal, so two wild nodes are separated by momentum 2k0. So that is the Hamiltonian for two wild nodes. So if I do the Boltzmann transport conductivity, so that results you can see from this current relation. So J is sigma 0 E plus alpha 1 some coefficient E dot B times B. So if you find out what is the conductivity from this relation, so it will be sigma 0 plus alpha 1 B square cos square phi and alpha 1 square B square sin square phi. So this is actually the relations what have been found by Boltzmann transport theory. But in wild semi-metals, so you have two wild nodes. Okay, so this property is coming why? Because E dot B is non-zero. So because E dot B is non-zero, because of the chiral symmetry broken things, you find this conductivity. So that is the key here, that you have E dot B is non-zero. All right, so that is the thing. But in wild nodes, what you find is that two wild nodes are separated along certain directions. So in principle, then there is a broken rotational symmetry. So if you have a broken rotational symmetry, so what are the possible terms that you will have in the current if you want to have the linear in electric field and quadratic in magnetic field? So this is the term that is same thing. So what 3 more terms you will get here, which is quadratic in B and linear in E. And that is because you have the rotational symmetry broken, and you have along z directions these 2 oil nodes are. So you have non-zero E dot z cross B also. So that gives you the conductivity as well. So because of the 2 scalars E dot B and E dot Z cross B, and the current propagation B and Z cross along B Z cross. Now let's say you equate the parameter alpha 4 equals to minus alpha 1 and alpha 3 equals to alpha 2. Then you find that sigma xx. So you'll have 2 terms here, and alpha 1 and alpha 2 is a negative sign, and then alpha 1 alpha 2 is a positive sign. So together you can see that sigma 0 plus sigma r cosine 2 plus phi of r, and sigma r sine of 2 plus phi plus r. So as you can see that there is a phase shift because of these 4 all these terms. What we find is there is a phase shift here, and if you have a phase shift, now it naturally explains the sign change of these conductivities. And so this is some argument from the symmetry principle, but we will have explicit calculations using a diagrammatic Kubo formula, and we will show that this is exactly has been found by the diagrammatic Kubo formula. Okay, so this is the diagram. So this is the diagrams that you all know. So this gives the conductivity. Now for the this is the electric vortices for the electric field. Now we have magnetic field. So these are magnetic field vortices. So in this case, this term and these terms actually becomes 0. So there will be no linear dependence on the conductivities, linear magnetic field dependence on the conductivities. So what we'll have is only the quadratic dependence in the lowest order. So you have the 2 vortices here, or the 2 vortices there, or 1 vortice is here and 1 vortice is there. So these 2 terms mutually cancels. So what we have essentially then this term gives the Drouet conductivity and topological conductivity, topological Hall conductivity. And there will be another diagrams where you will have the quadratic dependence on the conductivities, quadratic magnetic field dependence on the conductivities. Okay, so if you expand these response functions, so what we will find it as two form factors, phi 1 and phi 2, and then you take the gauge, let's say vector potential AZZ, that tells you that you have a magnetic field in the plane only. So this is the magnetic field in the plane. And so if you expand this, so we'll have 2 form factors, phi 1, phi 2, in the quadratic order of the Q. So this is the one term and the other term. And if you expand pi xx, so you have the same form factors, but with different coefficients here, pi 2 by 2, here it's pi 2, and there's a negative sign and these things. So now because of B is this, you can easily now convert that formula, and you find that sigma yx is sigma r sine 2 plus phi r, and sigma xx is sigma xx, which is the Drouet conductivity, is coming from this formula. So this is sigma r cos 2 phi r. So you can see that the Kubo formula actually gives these two expressions of sigma yx and sigma xx. And sigma r, that's the amplitude of this oscillation, is coming from these factors alpha 1 square, alpha 2 square, and the alpha 1, alpha 2 are actually related with these form factors. So sigma r is quadratic, b square, and there is alpha 1, these things, and this phase shift 2 phi r is tan inverse alpha 2 by alpha 1.
Say 5 more minutes.
Okay. So if you see it, how is the difference? This alpha 1 that I talked about, alpha 1, is actually the disorder dependent, is function of tau, but alpha 2 is actually the intrinsic. So it's a function of the OL node separation, this K0. So this alpha 1, alpha 2. And if I calculate the conductivities, so you can see that both the magnetoconductivity and the Hall conductivity. So you can see the magnetoconductivity, which is the red one. So you have from negative to positive. So there is a sign change, and of course this formula only gives. And there is a phase shift of a little bit of phi r. As you can see that there is a little bit of shift of phi r, and that phi r depends on this parameter tau tilde, which is tau tilde is proportional to the relaxation time tau, and K0, which is the wild node separation. So if you take that, the variations of phi r is like that. This. So there is a variations of phase difference depending on the disorder and wild separation scale. So okay, so according to that, you have the resistivity formulas similar like rho 0 minus rho r and rho 0 things, and we had these 3 sets of data where both rho xx and rho yx have been given. So we analyze those. So you can see here it's a data if I fit with these formulas. So you can see here, for example, here phi r from rho xx and rho yx is giving the same value. Similarly for this experiment 1.78, 1.78, and for this experiment, so you can see that it's 37 degrees, and this is also 37 and 35, 35 for different magnetic fields. So it agrees quite well with the experiment. All right, so these are the formulas, and the other experiments they have not given the full variations of rho xx and rho xy with theta, but they have said that there is a sign change in on the magnetoresistivity. So according to, if I take that, so the phi r corresponding to the phase shift corresponding to those systems will be like for this is 20 degree, 40 degree, 43 degree, 5 degree, 42 degree, and 35 degree. So this is less because this is the Dirac semi-metal. It's not Weil semi-metal, but that can be converted to Weil semi-metal for weak magnetic field perpendicular to that. So that is why it's a small angle, small phase shift. Other has larger phase shifts. Okay, so these are the main conclusions of my study. So you have a planar Hall and magnetoconductivities have novel intrinsic contributions. So you have, apart from the extrinsic, which is coming from the Boltzmann transport, but there is another component which is perpendicular to that, which is the intrinsic. And the planar Hall and magnetoresistivity are periodic with equal amplitude and phase shift, while they are of 90 degree phase difference, because one is sine function and the other is cosine function, but they have the same amplitude and same phase shift. And experimental data and planar Hall and magnetoresistance agrees well with our theoretical predicted form. Okay, so with that I stop.
Okay. Thanks, Professor Mohan, for the talk. So we have questions from the audience. No questions. In that case, if there are no questions, maybe we can thank the speaker once again. Thanks, Professor Mohan, for the talk.